Hello guys, we are back here with the phenomena of ringing in digital controllers. So whenever we design the controllers, we may come across a special phenomena, and in this session we shall be just deliberating upon what is ringing and how this ringing is determined by simply looking at the poles of the transfer function of any controller. So what we see over here, as you can see on the screen over here, we have the controller with the transfer function dz given by the output of the controller over the input, which is invariably error in case of controller. And let us say this is given by a very simple thing, 1 upon 1 minus p z to the power minus 1. This is perhaps the simplest possible controller which we can ever have, and in this case this p is the pole, and this value of pole we shall be determining, and we be seeing that we all know, we have seen that these poles for any system in discrete time, the poles should always lie in the unit circle. In the unit circle means the magnitude of the pole, it should not be more than 1 on either side of the polarity, means it should lie something between -1 and +1. If it is 1.2 or -1.2, so that's a clear-cut case of the system being unstable. So this is the first prerequisite we take into account, that this pole is lying within the unity circle, otherwise the system will become unstable. So there is no point in moving anything ahead of that, so we should not go for those kind of poles in any case. Now even if the pole is within unity circle, even if the system is stable, we may have this issue, what we call it as the ringing. Let us see how it happens, and for that what we will be doing is that we shall be taking some error, we shall be giving some impulse error. Impulse means that this error which is to be introduced over here in this controller, this unit impulse is given at t is equal to 0. Unit means its strength is unity. It means for all values of t less than 0, the error is 0. For all values of t greater than 0, the value of error is again 0. Only at t is equal to 0 we have a unit impulse, we have error which is equal to 1, and this is what we take it as the input. And in response to this error, in response to this impulse error which is given to this controller having the transfer function given by this, where we can vary the value of p and see how this controller responds to this impulse, unit impulse at t is equal to 0. So this is something very simple. In case you feel like taking a copy and a pencil or something of that sort to do some quick calculations side by side, you can do that also. I normally recommend in between, wherever you feel like pausing the video, you can pause the video and do the things again manually and then resume the video thereafter. So friends, we see that the output of the controller as given by this equation, what you have to do is you have to simply cross multiply. So this CZ will be multiplied by 1, and when I take the inverse of that, this will become Cn, as simple as that. And then this minus p, Cz is getting multiplied by minus p into z to the power minus 1. Z to the power minus 1 indicates that the signal is delayed by one sample. So it means that this p will not get multiplied by Cn, but it will get multiplied by Cn minus 1. This minus 1 has come on account of this z to the power minus 1. This is something very simple, you all know. And this error, it get cross multiplied to come over here in the form of En. So as we see that this equation becomes Cn minus p times Cn minus 1 is equal to error, and we're going to put the error for all values of t is equal to 0, 1, 2, 3, 4 and so on and so forth as the samples of errors are coming over, and we will take some value of p and then keep on changing the value of p to know the response of this digital controller in this case to see where actually ringing happens. So what we are doing over here, friends, you can all see that we have this error, it's equal to 1 for n is equal to 0, and for all other n's, that is n is equal to 1, 2, 3, 4, this error is equal to 0. It means it's an impulse. At t is equal to 0, you have unit impulse and it vanishes for all subsequent samples thereafter. So friends, I will say that we choose to start with the value of p is equal to minus 0.9. It has been deliberately set at minus 0.9. This minus 0.9 means that the system is stable. As such, if we see the poles are lying within the unit circle, the magnitude of pole is less than 1 as such. So we can very well safely say that it is not going to affect the stability of the system. However, we will see here that the moment we put this value of 0.9 over here, this value of 0.9, as we put it over here, and we have this value Cn plus 0.9 Cn minus 1 is equal to epsilon n. So to start with, we will take that the controller has no output to start with. So the moment at time t is equal to 0, this epsilon n comes equal to 1, this Cn becomes 1. Thereafter, when this Cn is 1 and this En as such will be 0 thereafter, and so this Cn minus 1 will become 1, and Cn in the next step, what will happen? In the next step, En will be equal to 0 and this Cn1 will be as determined previously, this was 1. So 1 multiplied by 0.9. So Cn in the next step will become equal to minus 0.9. I may repeat for your clear understanding that first of all, at t n is equal to 0, we had epsilon is equal to 1 and Cn minus 1 was not existing because we are assuming that initially the controller output is 0. So in that case, you will find that Cn is equal to 0.9 multiplied by 0 is equal to 1 because this epsilon n is equal to 1. From here we get Cn is equal to 1. Now once this is over, we go to the next step. This Cn in the next step will become Cn minus 1. And in the next step, the value of epsilon for n is equal to 1 in the next step, this will be 0. And we put the value of Cn minus 1 as equal to 1 as determined from the previous step. And from there, we get the value of Cn that comes out to be equal to minus 0.9. And then subsequently, this minus 0.9 in the next step will become Cn minus 1. So this process will continue and we will get a kind of table. We will plot a table and we will also plot a graph for this and see how this behaves for p is equal to minus 0.9. We will also discuss it for p is equal to plus 0.9 and then we see, compare and contrast what is happening over there in the next slide. As we had discussed in the previous slide, we have seen that for p is equal to minus 0.9, applying this equation, you can just make use of your copy and pen and or pencil and pause the video and see whether you can verify this table or not. At n is equal to 0, epsilon n is equal to 1 and epsilon n vanishes thereafter because it's only a unit impulse, and for that we got Cn is equal to 1. So this Cn is equal to 1 in the next step, that becomes Cn minus 1, and then we calculate the value of Cn, you will get minus 0.9. This we had seen, and as you go on doing it subsequently, you will find that in the next step the value of controller output is plus 0.81, then it becomes minus 0.729, then it becomes plus 6.5, then it becomes minus 0.59 and so on and so forth. So you see that the output of controller is continuously varying from the positive sign to the negative sign to the positive sign to the negative sign to the positive sign, and so on and so forth. However, if you take p is equal to plus 0.9 and put this value of p in this equation over here, and again with the help of copy and pencil or pen, you again compute as per the value of epsilon n. Subsequently, the value of cn minus 1 will be coming over here. You will find, you have to verify it on your own, you will find step by step that the controller output is changing from 1 to 0.9 to 0.8 to 0.7 to 0.6 and so on and so forth. There is no change in polarity of the output of controller. This is something very important. This is something very important. Here the polarity of controller is changing. It means that if I take the range of controller from -1 to +1, -1 means controller is totally giving output. It's asking the final control element to be totally closed. -1 means 0% open, and +1 means 100% open. Let us say, in that case, what will happen? You will have at 0, you will have controller asking the final control element to be 50% open. So in that way, if you can visualize, if you can just understand what I'm saying, 1 means controller is fully open, -1 means controller is fully closed, -0.9 means controller is only 10% open, and over there, as you can see, with +0.8 as such, it means that the controller is something like 80% open, and so on and so forth. So what you see, if you plot it, you will see that as the controller is moving from 1 to -0.9 to +8 to -0.7 and so on and so forth. If you tabulate it, you will see that at one step the controller is 100% open, then it goes down to almost close, just 5% or so, and then you have almost open, that is almost 90% or so, then it again is almost close to something like 15% open, and so on and so forth. So there is very fast and quick motion of control output, which is making the final control element move from almost fully open to fully closed to nearly fully open to nearly fully closed, and so on and so forth. So it's not possible for the final control element to follow this kind of instructions coming from the controller. It's very difficult, and we say that this controller is not suitable for most of the practical applications. This phenomena of the output moving from positive to negative to positive to negative so frequently is called ringing. The controller is said to be ringing, whereas for the positive poles of, let us say, 0.9, here you see the output is changing, no doubt, but it is changing smoothly from 1 to 0.9 to 0.8 to 0.7 and so on and so forth. And we will see this in the next slide graphically also. This controller is not ringing because it's changing smoothly, and here the output is changing after every one sample. It means that if the sample time is, let us say, 1 second, then it is physically not possible for the controller to move in 1 second from almost fully open to almost fully closed. It's not possible. We say we avoid this kind of situation. We say the controller is ringing. We don't want this kind of controller. And friends, this successive change in the sign of the controller output, once again I may say, is called ringing. And we have also seen that this is caused by negative poles. It was not there for p is equal to plus 0.9. It was there only for p is equal to minus 0.9. So what do we see? What do we see in this slide? You can see that for the value of p is equal to minus 0.9, the controller is ringing from here to here, the plus up, the minus, plus up, and minus, and so on and so forth. Every 1 second, if t is equal to 1 second, it's just ringing like this. It is not a very good situation. Whereas for p is equal to plus 0.9, the controller output is changing very gradually, very slowly in the same direction, and it's quite possible for us to move the controller from, let us say, fully open to 50% open in 5 seconds time. It's quite possible. In case P is negative and let us say minus zero point 0.3, again you can see the ringing taking place over here also. In case this is positive T, the controller output required is quite sharp and fast, but still it is not ringing. So what do we come to the conclusion? We come to the conclusion that this is the best possible pole. This is the best possible pole. It means that for the output to be followed by a final control element, for the output of any controller to be followed by the final control element, this pole should be number one positive. It should not be negative, otherwise you will have a situation like this. And number two, it should be as close to 1 as possible, 0 0.9, 0.95 or 0.89, 0.85 and so on and so forth. Because as it becomes nearer to, although it is positive, as it becomes nearer to 0, the change which is being introduced may not be followed by the controller in such a sharp manner. Therefore, this is the best pole. It is not having any ringing. It is quite stable also, and it is near to 1. So this is what we have learned in today's session. Whenever we shall be designing the poles for a particular controller, which is not to be done in this session, maybe you will be learning in higher courses like advanced control systems and so on and so forth. We have to see that the placement of the pole for the controller should be number one within unity circle to ensure its stability. Number two, it should be positive to avoid ringing. And number three, it should be as close to unity as possible so that the changes are gradual and they can be easily followed by the controller output given to final control element. This is the last thing to be discussed in this session, and this is what is summed up pictorially over here, that you have the poles if they are outside the unit circle. If let's say pole is here or pole is here or pole is here or pole is here, in that case the system will become straight away unstable, not desirable. In case the poles are within the unit circle but they are in the negative side of the circle, in that case the system as such is stable, but this is going to give what we call it as ringing poles, especially for the controllers. We don't want this ringing for the reasons I have already told you. So these kind of poles should also be avoided to the extent possible. So the desired poles are somewhere lying in this region, and here also this pole is slightly better than this pole. And if you have somehow placed pole over here, this pole will be even better because nearer to the unity the change is gradual and therefore easy to implement. So this was about ringing in digital controllers. I hope you have understood this phenomena. In case you have any queries or observations, you can contact me either through phone or you can ring me the way you feel like on WhatsApp or whatsoever. So I will not mind that kind of ringing. So we will discuss more on ringing in that case, and hope you have enjoyed the learning. I thank you for being with me once again, and I wish you a very safe stay. Bye bye.